All right, let's take a look at our sixth example problem from chapter 6. Water is throttled from 20 bar, 20 degrees C to 1 bar. What is the final temperature? So we have a throttling process. So this would be water flowing through, say, an orifice, venturi meter, or partially closed valve. Okay, and so schematically, I'm going to draw this. This device, this flow device would be my venturi meter, orifice, or partially closed valve. Coming in, I'm going to have some inlet stream. I'll call it T1 is at 20 degrees C. And P1 is equal to 20 bar. Okay, and exiting, my system is going to be at a pressure of 1 bar. Okay, so I'm reducing the pressure. We're not told what T2 is. Yeah, so this is all we're given. Okay, so my inlet state's fully characterized, right? I have two intensive properties. In terms of my exit stream, I have P2, right? So I only have, one parameter specified. So unless I'm at two-phase coexistence, right, that is not fully specified. All right, but hopefully let's see if we can find it from our energy balance. Okay, so so we have to calculate T2. All right, so we'd see if we could find it from our energy balance or our entropy balance. I'm going to go with our energy balance because as far as our entropy balance is concerned, unless I assume Sgen is equal to 0, right, I'm not going to be able to make any progress on that. Okay, so I'm going to start with my energy balance, and so I start by writing my so I'll make this part A. So I'm going to start by writing my general first law balance for my open system. So du total dt plus delta, and then we have kinetic energy, v squared over 2, plus potential energy, plus enthalpy. Remember, enthalpy and not internal energy, because my fluid element needs to displace the fluid element in front of it, so it's H and not U. And that's going to be equal to G plus W. Okay, so I always start by writing down my general first law balance, and then it's a matter of simplifying. Okay, so let's simplify. So the first simplification I'm going to make is I'm going to assume steady state behavior. So by assuming steady state behavior, my accumulation term, du total dt is equal to 0. And then I'm also going to take it that my inlet and outlet mass flow rates are exactly the same. Okay, my mass flow rate's constant. There's no accumulation of mass occurring inside my system. Okay, so I'm going to assume steady state. Okay, 2. And so, these first two assumptions, steady state, we'll pretty much always assume unless we're told otherwise. And same thing for 2, we're going to assume that our change in kinetic and potential energy is negligible. Okay, so we're going to assume change in our kinetic energy and potential energy are negligible. Okay, so that would kill this term and this term. And then the last assumption I'm going to make for my throttling process, so this will be unique to throttling, is, well, one, so throttling is going to correspond again to an orifice, a venturi, or partially open valve. So I'm going to have my fluid flowing through some restricted space. So I'm going to assume that there's no shaft work present. So I'm going to assume that W dot is equal to 0. And then I'm also going to assume that there's no heat being exchanged between my system and surroundings. Okay. So one, I'm going to assume that there's no shaft work, there's no work being done on my system or by my system during this expansion. And then 2, right, I'm going to assume that it's adiabatic, okay, that there's no heat exchange between my system and surrounding. Okay. And so when I do that, my first law balance reduces to, so I'll just have, well, H2 minus H1 is equal to 0. So therefore, H2 is equal to H1. Okay, So this is great. So since T1 and P1 are known, the inlet conditions of my stream are known and specified. So I should be able to go to my steam tables and read off all of my thermodynamic properties. And then since I know H2 is equal to H1, so then I'll know H2 and P2, the exiting conditions of my stream are also specified. And so I should be able to use that to find the corresponding temperature. All right, so let's do it. Okay. So, let's collect some thermodynamic properties. Okay. So again, my inlet is at 20 degrees C and 20 bar. Okay, that's 20 degrees C and 20 bar, and my exit's at 1 bar. Okay, so let's start by finding some thermodynamic properties for our systems at 20 degrees C and 20 bar. Okay, so my steam table should be hiding behind this page. Okay, here we go. So let's look at 20 bar. So this is my superheated steam tables. So at 20 bar, my saturation temperature is 212.38. So my temperature is less than Tsat at that pressure. So I have a compressed liquid. So my inlet is going to correspond to a compressed liquid. Okay. Now if I use, enthalpy just symbolically as my example. Okay, so in general, when we're trying to pull properties from our compressed liquids from the steam tables, right, when we're not given other information in the problem statement, okay, the assumption we're going to make is that, say, my enthalpy of my liquid at T and P is going to be approximately equal to the enthalpy of the corresponding saturated liquid at the same temperature, but the corresponding saturation pressure for that temperature. Okay, so what does that mean? Okay, so if I wanted to look up H1 and I'll collect S1 when I'll add it, just in case I need it. So I will actually go, so we're at 20 degrees C. So instead of my superheated steam tables, I'm going to go up to my saturated steam tables, which is tabulated in terms of temperature. Okay, I find 20 degrees C, and so saturation pressure is 0.02 bar. So basically I'm assuming that my properties at 20 degrees C and 0.02 bar are approximately the same as my liquid at 20 degrees C and 20 bar. And so it's a pretty big stretch, but pretty big difference in pressures, but based on the information given, that's honestly the best we can do. So we'd find the enthalpy of the liquid is 83.92. So this could be H1 is 83.92. That's kilojoules per kilogram. And then S1 is 0.2965. So it's 0.2965. That's going to be kilojoules per kilogram Kelvin. All right. So in terms of my exit stream, so it's going to be at a pressure of 1 bar. And I know that H2 is going to be equal to H1, and that'll be equal to 0.83 0.92 kilojoules per kilogram. So now I'm going to go to my superheated steam tables, because that's incremented in pressure. Okay, and what I'm looking for is an enthalpy of 83.92. Okay, so I'm looking for an enthalpy of 83.92. Okay, and we are off the charts, right? So the enthalpy of my liquid begins at 417, okay, 0.44. Okay, so now at 1 bar, the corresponding saturation temperature is 99.61. So what that tells me is my temperature is less than 99.61 degrees C. All right, so I'm not just going to be able to go to my saturated steam tables and look for that corresponding enthalpy. Okay, so at 1 bar, my temperature is definitely less than the corresponding saturation temperature. Okay, and so again, if I look at 1 bar, enthalpy of the liquid's 417.44. All right, then we jump up into the 2000s once I have when I look at the saturated vapor and then superheated vapor. So I'm definitely, I'd be way to the left. Okay, so we're going to have a compressed liquid. Okay, so our temperature is definitely going to be less than that corresponding saturation temperature. And so again, we're going to have to make this assumption. If I make enthalpy, use enthalpy as an example, that essentially we're going to have a liquid and we're looking for the temperature for which the saturated liquid has, this enthalpy, which we would take to be that of the compressed liquid. And so, if I were to go to my saturated steam tables, right, and I'm looking for this HL of 83.92, right, where it's going to occur is at 20 degrees C. Okay, so for our compressed liquid, right, it has to be then, we're going to find that T2 is equal to T1 is equal to 20 degrees C. And, we would get the same, H2, and then S2 would be equal to S1, of course. So for the case of a compressed liquid, so if we're throttling a compressed liquid, we're assuming that there's no work done, which is good, and that there's no heat exchange between our system and surroundings. We get, for this case of a compressed liquid, that the inlet and outlet temperature are exactly the same. Okay, that there's no change in temperature. Okay, that's cool. Okay, but I guess we chalk it up to fluids class, but you do get a decrease in your pressure. Okay, so you do get a pressure drop. So there is some, so you do get a pressure drop, but we'll leave that for your fluids class. All right, and then we're asked to repeat if the final pressure is instead 0.00706 bar. Okay, so in B, okay, we're going to repeat. Okay, but what's going to differ, okay, is now we're told that P2, okay, so I'm just going to keep it the same. P2 is now 0.00706 bar. 0.00706 bar. All right, that's pretty small. And again, we're going to have H2 is equal to H1, and that's equal to 83.92 kilojoules per kilogram. All right, so let's go back over to our steam tables. 0.0076. Okay, so that's 00706. Okay, so 1, okay, if I just so happen to look at my saturated steam tables, I get 0.00706 appears as a saturation pressure for a temperature of 2 degrees C. Now, if I read across, let's see, my enthalpy is definitely between the enthalpy of the liquid and vapor phase at that pressure. So I find that it just so happens I have a PSAT of 0.00706. And just for comparison, if I go to my superheated steam tables, right, the lowest pressure is 0.05. Okay, so presumably they took this problem or pressure from put this pressure on the problem, for a reason such as this. So I find saturation pressure of 0.00706 happens at a temperature of 2 degrees C, and my enthalpy is between these two. So it must be that I have a two-phase system. Okay, so my temperature is 2 degrees C. Okay, then scrolling down, I want to record the enthalpy of the liquid and the vapor. Okay, I guess they don't ask us to calculate it, but so the final temperature is 2 degrees C. Okay, because, so this is my saturation temperature at a pressure of 0.00706. And if I look up the enthalpy of my liquid and vapor, okay, we get the enthalpy of the liquid is 8.39, and that's kilojoules per kilogram. And the enthalpy of my vapor is 2504.6. All right, so at that pressure, all right, I find that my enthalpy is between the enthalpy of my saturated liquid and vapor, so I must have a two-phase system. And if we want, we could go ahead and we could compute the quality. And so the quality, rather than derive the equation, right, we should, sure it's probably beat it in your head by now, but essentially we would have that H2 is equal to, okay, the fraction that's vapor, which we call the quality, Q, times HV plus 1 minus Q times HL. Okay, so let's solve for Q. So we get QHV plus HL minus QHL. So H2 minus HL is equal to Q times HV minus HL. So therefore we get that the quality Q is equal to H2 minus HL divided by HV minus HL. Okay. So for completeness, let's compute the quality. Okay. So let me bring up MATLAB, which should be behind here. Okay. And so enthalpy of stream 2 is 83.92. The enthalpy of my liquid is 8.39. The enthalpy of my vapor is 2504.6. Okay, and just based on this, right, we expect it to be mostly liquid, given how big the enthalpy of my vapor is. Okay, but anyways, Q would be H2. Let me make sure I get H2 minus HL divided by HV minus HL. So H2 minus HL divided by HV minus HL. So let's save this. Okay, run it. We get a Q of 0. Q being the quality. So let me put like qual on here just so I keep track of it. Get a quality of 0.03. Okay. And so the quality is 0.03. So it's still mostly liquid. So it's mostly liquid. A tiny little amount of vapor is formed, but our temperature is at, our temperature would be 2 degrees C. Okay. So hope that helps. So for our throttling device, we assume steady state, change in kinetic and potential energy is negligible, and that our work and heat terms are 0. Okay, cool. And if you want to calculate entropy generation, since we're assuming Q is 0, then we get S gens just equal to delta S of my system. And so for the first case, we would get actually an S gen of 0, since delta S of our system would be 0. Okay, but for the second case, that wouldn't be the case. Well, we can. Well, let's see. So the problem is asked is solved for. But let's calculate S gen in these two cases, right? And so if I take an aside, okay, in the first problem, right, S gen is going to be equal to delta S of my system plus delta S of my surroundings. Okay, where we're assuming adiabatic, so delta S of my surroundings is going to be 0. And so we end up with S gen is equal to S2 minus S1, which in this case is going to be 0 since the entropy of my two states are the same. Assuming that we have this compressed liquid and that we're estimating the properties of my compressed liquid is that of a saturated liquid at the same temperature. So, that's coming down to assuming we have a compressed liquid and it's incompressible. So if you were to look up, let's look up the entropy of my liquid and entropy of my vapor. Okay, then we can calculate S2, and let's compute the difference for that case. Okay, so that is behind here. So 2 degrees C, S of my liquid is 0.0306. 0.0306 kilojoules per kilogram Kelvin, and SV would be 9.1027. So 9.1027 kilojoules per kilogram Kelvin. Okay, so S2 would be Q times SV plus 1 minus Q times SL. Okay, so let's go ahead and let's compute S2. Oops, I've got to bring MATLAB back up. Okay, so this is, there we go. So clicker wasn't working there for a second. So we had SL was 0.0306, SV 9.1027, S2 then would be equal to Q times, well, I call it qual, times SV plus 1 minus the quality times SL. Okay, and then let me record S1. S1 was 0.2965. Okay. So then we end up with Sgen is equal to S2 minus S1, right? Let's see. So we'd get an entropy generation that's positive. So it's pretty small. It's 0.0086. All right, so we get an Sgen of 0.0086. That's kilojoules per kilogram Kelvin. Okay, but in terms of estimating this entropy here, right, we're assuming that we have a compressed liquid and that at 20 degrees C and 20 bar, our properties of our liquid are approximately the same as at 20 degrees C and pressure was much less than 1 bar. Okay, so we are making some assumptions here, but the problem didn't ask for entropy generation, but it is pretty interesting. So in the second case, we do get a small positive entropy generation. In the first case, we don't, and that's mostly inherent in that we're assuming that we have this incompressible fluid. So anyways, hope that helps. We'll see you in the next example.